Let us see this problem. We are given two sorted arrays. We need to find out median of these two sorted arrays. Let's consider this example to understand the problem. We have first sorted array with elements 10, 20, 30, 40, 50 and second sorted array as 5, 15, 25, 35 and 45. Now if I combine these two sorted arrays and make one sorted array, whatever element or elements come into the middle are called median. In this case, we have two elements in the middle. Half of the elements are smaller than these two elements and half of the elements are greater than these two elements. These two are the middle. So our answer is average of these two elements, which is 25 plus 30 by 2. So we have written 27.5 as our answer. Let's now see the second example. In this example, again we have two sorted arrays, and if we put all these elements together in one sorted array, we'll get 1, 2, 3, 4, 5, 6, 10, 20, 30, 40, 50. And this time we have total odd elements. So there is going to be one element which is greater than half of the elements and smaller than half of the elements. And this element here is 6. So our answer is 6.0. Let's now see the third example. If we put all these elements together in one sorted array, we are going to get this 1, 2, 3, 4, 5, 10, 20, 30, 40, 50, 60. And among all the elements, you have 10 as the middle element because there are total odd elements. You will have only one middle element, which is a median. So our answer for this input is 10.0. Now please pause this video and think of an approach to solve this problem. Let us first talk about naive solution to solve this problem. We create an array temp of size n1 plus n2. We copy the elements of a1 to temp and then copy the elements of a2 to temp. Then we sort temp, and after sorting it, we check if n1 plus n2 is odd. Then we return the middle element of temp. Otherwise, we return the average of middle two elements. For example, if a1 is 10, 20, 30, a2 is 5, 15, 25. First we copy a1 into temp and then we copy a2 into temp. Now we sort the temp. So after sorting, our temp becomes this. Since there are even number of elements in the temp, we return the average of these two elements. The time complexity of the solution is n1 plus n2 into log of n1 plus n2. This solution can be optimized. We can use the merge process of merge sort that we are going to discuss in sorting track, and we can make the solution in big O of n1 plus n2. But can we do even better? Can we do better than the linear time complexity? Can we solve this problem in logarithmic time? Now please pause this video and think of a solution that works in logarithmic time. Let us see the efficient solution now. The idea is to use binary search. So we are given two sorted arrays, a1 and a2 of size n1 and n2, and we need to find the median in this question. In this implementation, we are going to assume that a1 is always having size is smaller than or equal to a2, which means n1 is smaller than or equal to n2. Now if user provides first array as of greater size, then you can always swap the pointers in C++ and swap the references in Java and make sure that a1 is smaller. But in the explanation going forward, we are always going to assume that a1 is a smaller size. The time complexity of the solution is big O of log n1. So we do our binary search in the smaller sized array, and we begin our binary search from middle of a smaller sized array. During the binary search, we maintain two sets, this set and this set. The first set contains some elements from left side of a1 and some elements from left side of a2. The other set contains some elements from right side of a1 and some elements on right side of a2. During binary search, we ensure that in every iteration, the left set contains exactly half of the elements and the right set also contains exactly half of the elements. If there are odd elements, then we can have one extra element in the left half. So now we know we need to do binary search in the first array, and we need to maintain these two sets such that half of the elements are in the left set and half of the elements in the right set. How do we find out index in the other array so that we can have exactly two sets of half elements? We can use this formula for this. If you know the current index in first array, and you want to divide all 14 elements, 5 plus 9, 14 elements into two half of sets, 7 elements, then you can find out I2 using this index. So I1 is beginning of the right set in the first array, and I2 is the beginning of right set in the second array, this particular set. So for example here, I1 is 0, 1, 2, and N1 is 5 and N2 is 9. So what do we get as an I2? 5 plus 9, 14, plus 1, 15, divided by 2, 7. So we will take 7 minus, what is I1? I1 is 2 here, right? 7 minus 2, which is 5. So we have I2 as 5, 0, 1, 2, 3, 4, 5. That's how we get the I2. We can always use this formula to get the beginning index in the second half of the right array. And our whole purpose is to have equal elements in the left half set and right half set. This formula here takes care of both even and odd elements. You can try this using pen and paper, and you will see that whatever value you pick for I1, you will have corresponding value for I2. So now we have discussed this much, that we are going to do binary search on the smaller array, and our first array is always going to be the smaller array. And we are going to pick index in the second array such that we have equal half elements in the first half and equal half elements in the right half. Now, how do we do our binary search? When do we decide that we need to stop here? We have found the median. And when do we decide that we need to go to the left half? And when do we decide that we need to go to the right half in the smaller array? Now, to see the stopping condition, let's modify this array. Let's say we have these elements as 27 and 28. Say this is your array. And you began your binary search from here. So this I1 was here and I2 was here. Now at this point, if you see, you can notice that all the elements in the left half are smaller than all the elements in the right half. All these elements, 10, 20, 5, 15, 25, 27, 28. These elements which are in the left half set, they are all smaller than all the elements in the right half set. What it means is, you have found the point where your median lies. You have half elements small on this side and half elements greater on this side. So if you just pick largest element from this set and smallest element from this set, and if you take the average of these two elements, you will have the median. And to pick the largest element from this set, it's easy because these arrays are individually sorted. Largest of this is going to be 20, largest of this is going to be 28. And maximum of these two is 28, right? And to pick the smallest of this side set, we will pick the minimum of 30 and 55, which is 30. So your median is going to be 28 plus 30 divided by 2. So if you reach a condition when all the elements in the left half are smaller than all the elements in the right half, then you have found the median. And that's what binary search tries to achieve. It tries to achieve a situation where you have all the elements in the left half smaller or equal to than all the elements in the right half. I have modified the second array again and written back the original values. Now consider that you begin your binary search with these arrays. Your I1 is here and I2 is here. What do you decide now? Should you be going to the left half of array 1 or should be going to the right half of array 1? And how do you decide? You want to achieve a situation where this set or these blue marked elements have all smaller values and this side has all greater values. But that's not true here because this 35, which is in the left half, is greater than 30, right? So this 30 is actually a smaller element which has gone to the right side. So you will do binary search in the right half of a smaller array. When you do binary search in the right half of a smaller array, whatever index you reach, you can find the corresponding index in the other array using this formula, same formula. So that's the basic idea of this binary search based algorithm. Let me do a quick recap of the algorithm that we have discussed so far. We are going to do binary search in the smaller array. Whatever index we are at in the smaller array, we can find out corresponding index in the larger sized array using this formula. During binary search, we are going to maintain two sets. First set contains elements from 0 to I1 minus 1. The other set contains elements from I1 to N1 minus 1 from A1. And from A2, the first set contains elements from 0 to I2 minus 1 and the other set contains elements from I2 to N minus 1, right? And these arrays are sorted, but during the binary search, it might happen that this side does not have all the smaller values. And by comparing the middle values, these four values, I1 minus 1, I1, I2 minus 1, and I2, by comparing these four values, we can decide whether we have reached the median, or we should be going to the left half, or we should be going to the right half. So I have not discussed the complete logic. Please pause this video now and try to write down a complete binary search algorithm or program that handles all the cases. Before you write the code, it is strongly recommended to do some examples using pen and paper. Let us now talk about C++ and Java implementations of this efficient approach. So in this implementation, we are doing binary search over the array A1. So we have begin 1 and end 1 as the current begin and end indexes of the array A1. And then we are maintaining these four extra variables, min1, max1, min2, and max2. Please note that, as we discussed earlier, we are going to maintain two sets which are of equal size, and the first set is going to contain the left elements of A1 and left elements of A2. And the second set is going to contain some right elements of A1 and some right elements of A2. And we stop our binary search when all the elements in the left side are smaller than or equal to all the elements in the right side. So we maintain these four variables which are boundary elements for the left and right subarrays. The min1 element is the beginning of right side of A1, and min2 is beginning on the right side of A2. So this is what the structure is. You have two arrays A1 and A2, right? And then you have an index I1 that tells you the beginning of right side, and I1 minus 1 is the index that tells you beginning of end of the left side. In the array 2, which is probably of the larger size, you again have an index I2, right? And this is the point where your right side begins. And on the left side, you have I2 minus 1. So the element which is at index I1 is the minimum element in right side of A1, and we call it min1. The maximum element on the left side is at index I1 minus 1, and we call it max1. Similarly, the minimum element, so this is I2 minus 1. Similarly, the minimum element in right side of A2 is called min2, and maximum element in the left side of A2 is called max2. And using these four elements, we are going to run our binary search. By comparing these four elements one way or the other, we are going to decide whether we need to stop our binary search at this point, or we need to go to the left half of A1 or go to the right half of A2. Let's understand this with this example. We first compute mid of A1, right? Which is our I1, begin 1 plus end 1 by 2. So begin 1 is 0 and end 1 is 3. So 0 plus 3 by 2 is 1. So that's what our I1 is. Now using I1, we compute I2. And what was the idea for computing I2? We should have exactly half elements in this side and exactly half elements in the other side. So that's how we computed I2. I1 and I2 are the beginning indexes of the right side. And the elements stored at these indexes are called min1 and min2. And the elements which are just before them are called max1 and max2. So this is a max1 and this is a max2, right? So min1 is 20, min2 is 35, max1 is 10, and max2 is 25. Now take a look at these four elements, and using these four elements, can you decide whether you should stop your binary search or you should go to the left half of this array or right half of this array? Now if you compare 20 with 25, you can notice that 20 is smaller than 25. So your left side, which is these three elements and this element, they are not all smaller than or equal to all the elements on the right side. So this element is actually smaller, right? It should have been greater. So we go to the right side of it. That's how we decide that we need to go to the right side. Now let's see the code. How does this decide whether you should go left side or right side or you should stop? So we compute the mid index in A1, and using this value I1, we find out corresponding index in I2 such that we have two sets of equal sizes. Now we find out these 4 elements. So when we are finding out these 4 elements, we might have some corner cases that there is nothing in the left side, nothing in the right side, right, in A1 and A2. So that is why we have these ternary operators. If I1 is equal to N1, that means there is nothing on the right side. So in that case, we have our min1 as int max, infinite. And in Java, we have it as integer.max value. Similarly, if there is nothing on the left side, we have our max1 as int min, minus infinite. Otherwise, we have them as a1 of I1 minus 1 and a1 of I1. And similarly, we define min2 and max2 for A2. So we have computed these 4 values at the first step, and these are our 4 values. After that, we check if max1 is smaller than equal to min1 and max2 is smaller than equal to min1. Let's see this example. So our I1 initially was here, right? And I2 was initially here. And these are our min1, max2 values. So we are checking if 10 is smaller than equal to 35. This is true. Now we check if 25 is smaller than equal to 20. This is not true, right? So we do not fall into this condition. So we do not stop our binary search at this point. Suppose you had an element like 27 here, then you would have stopped your binary search here, because then you have all the elements in the left side smaller and all the elements in the right side greater. So we do not stop our binary search at this point. Now what we do is we decide whether we need to go to the left half or we need to go to the right half. The same thing we have in Java. And how do we decide? See, we did not stop our binary search because one of these 2 conditions were not true. If this condition was not true, if max1 was not smaller than equal to min1, min2, then we'll go to the left half. And if this condition was not true, then we'll go to the right half. That's what we have written here. If max1 is greater than min2, then we go to the left half. And if max2, else part will be that condition only, although we have not written. If max2 is greater than min1, then we need to go to the right half, right? And see, what is the condition here? It's not these 2 variables which are not following the rule. They were following the rule here. These 2 variables were not following the rule, 25 and 20, right? 25 is actually greater than 20, right? So that's why we go to the right half of this array. So when we go to the right half, we change our begin as I1 plus 1. So our begin becomes now, it was earlier 1, now it becomes 2. And our end remains 3. So now we begin our iteration here again from the beginning. In this second iteration, these are our values. We have begin as 2, end as 3, I1 as 2 plus 3 by 2, I2 as this formula n1 plus n2 plus 1 by 2 minus I1. So we get 2. And we have min1 as 30. This is the min1, beginning of the right side. Max1, end of the left side. Min2, beginning of the right side of A2. Max2, end of the left side of A2. Right? So we have these 4 values. And now we are again going to check for these conditions. So max1 is smaller than equal to min2. What is max1 here? Max1 is 20 and it's smaller than equal to min2. We are right here. Now max2 is smaller than min1. What is max2? Max2 is 15 and min1 is 30. So max2 is smaller than equal to min1. So we have reached the right point. And you can notice in this array, elements in the left half, they are all smaller than elements in the right half. So what we do here now is, we check if we have total even elements in the array. If we have total even elements in the array, then we need to return average of the middle 2 elements. And if there are odd elements, then we need to return the middle element. So here, if you see, we have total even elements. We have 3 plus 3, 6 plus 2, 8. So we fall into this case. Now, how do we find out the middle 2 elements? See, this is your left side. You have 2 sets. This is the left side, this is the right side. So to find the middle element, you need to find the maximum in the left side, and maximum will be maximum of these 2, right? Maximum of max1 and max2, right? Max1 and max2 are 20 and 15. So we simply take the maximum of these 2 as 20. Now we take the minimum of min1 and min2. Min1 and min2 are 25 and 30, and minimum of these 2 will be 25. So our median is 20 and 25, average of these 2, right? That's what we computed here. So 20 and 25 average is 22.5. So that's how we find out the median. With the same code in Java, we are using mat.max function here. And for infinite, positive infinite, negative infinite, we are using max value and min value. Let us see one more example for better understanding of this algorithm. Let's say we have this array A1 and this array A2. A1 has 4 elements and A2 has 5 elements. We initialize our begin and end. Begin 1 is 0 and end 1 is 4. Now we compute I1, which is begin 1 plus end 1 by 2. So we have 2. Now we compute I2 inside this loop, which is n1 plus n2 plus 1 divided by 2 minus I1. So we have it as 3. So once we have computed I1 and I2, we segregate our left side and right side. So these 2 elements are in the right side, these 2 elements are also on the right side. And these 5 elements are in the left side. And as we said earlier when we were discussing algorithm, if we have total odd elements, then this division happens this way, that your left side has 1 extra element. Right, so that's you can see, right? You have 5 elements in the left side, these 2 and these 3, 5. Now we have min 1, max 1, min 2 and max 2. Min 1 is beginning of the right side in array 1, 50. Max 1 is ending of left side in A1. Max 2 is ending of left side in A2. And min 2 is beginning of right side in A1. So we have these 4 values, and now we check, have we reached the median or not? If not, then we need to go to the left side or right side. To check whether we have reached the median or not, we compare these 2 things. Max 1 should be smaller than equal to min 2, and max 2 should be smaller than equal to min 1. So max 1 here is 40, and it's not smaller than equal to min 2. So this condition violates, so we have not reached the median. We need to either go to the left half and right half. And you can notice that all the elements in the left side are not smaller than all the elements in the right side. These elements are greater than these elements, right? So we need to either go to the left side or right side. Now, how do we decide whether we go to the left side or right side? One of these 2 conditions must have been violated, and we see which condition is being violated, and accordingly we decide. So if max 1 is greater than min 2, right? What is max 1? Max 1 is 40. It's greater than min 2, right? So we need to go to the left side. And you could notice this from this example. You have an element 50, you were doing binary search here, and this 50 is greater, but this 40 is also greater than 8. So your median must be lying on the left of it, right? Because these elements are greater than these elements. So we go to the left side, we again begin our iteration, we have begin and end. Now we compute I1 and I2. And this time I1 and I2 come out this way, that your I1 is 0, which means your right side begins with the first element itself, and your I2 is 5, which means your right side of second array begins beyond the last element. So everything is in the left side. So you have all the elements of first array in the right set and all the elements of the second array in the left set. And you can notice that your left set has 1 extra element. Now we again compute min 1, min 2, max 1, max 2. So what is our min 1? Min 1 is the element at index I1, which is 30. And what is max 1? Since I1 is 0, we fall into this case and we initialize our max 1 as minus infinite. Similarly, in this second array, min 2 is plus infinite because we do not have anything at index 5. Our I2 is equal to n2. So these are the values we have now, right? And now we check for this condition. Have we reached the median? Let's compare these 2 values. Max 1 is smaller than equal to min 2? Yes, it is. Min 1 is greater than equal to max 2? Yes, it is. So we have found the median. We have reached the median. And you can notice that all the elements in the right side are greater than all the elements in the left side. And you've reached the median, right? This code also tells us the same thing. So now we check, do we have total odd elements or even elements? In this case, we have total odd elements. So we are going to have only 1 median. And how do we find out the median in this case? We take the max of max 1 and max 2, right? Why are we taking max of max 1 and max 2? Because your median must be there in the left side, right? Because left side has an extra element. And if both the arrays have some left side, we need to take the maximum of these 2. We need to take the maximum of the left side. So maximum of the left side is here, maximum of 9 and minus infinite. Because this array does not have any left side. This particular array does not have any left side. So we have minus infinite for this array. So our overall result is 9. That's how we find out median for this particular example. Let's now quickly talk about the time complexity. We are doing binary search in array A1, and every element that we search in every iteration of this loop or this loop in Java, we do constant amount of work, right? We do some comparisons, find out the min and max of few values, and then do some, all these is called constant computations, dividing by 2, then doing subtraction, additions, and then doing some comparisons, then again doing some comparisons. There are no loops inside this while condition. So all that is constant work, and using constant amount of work, you decide whether you have found the median or you need to recursively call for the left half, or change begin one and end one iteratively, or you need to go to the right half, right? So its overall time complexity is clearly big O of log n1.